Hello and welcome to the Tau Manifesto Control Award. These are the following goals we've tried to achieve throughout the season. By the end of this video, we'll go through how we implemented these goals in our final product. This is an autonomous path planner that we created to quickly generate code. This planner maps a robot and its movements onto a field by taking user input, recording the movements the user inputs, then from that, figuring out the distances and angles, decomposing it into its parts, and generating code. As you can see, it also maps the robot's movements and past positions, allowing us to communicate our paths to our partners by creating a diagram. This path planner has streamlined the process of writing code from a matter of weeks to just a couple of minutes. It usually runs first time, and the code can just be copied and pasted into our program. It also automatically angles for shooting, accounting for distance, and curvature and RPM. This is a segment of code that you previously saw drawn out in the path planner. The path planner generated the code, and the robot is now executing. The smooth and exact movement you see is a result of proportional control, which includes acceleration and deceleration functions. This allows the robot to be extremely accurate during the autonomous period. To detect rings in autonomous, we created an autonomous pipeline. This pipeline starts with a normal picture, as you can see on the left, and then converts it to a bitmap, which is an array of pixels, each with a BGR of blue, green, red value. However, BGR represents light as a combination of the three values, and therefore it is very hard to threshold these pixels for all light conditions. Therefore, our second step in the pipeline is to convert to HSV, hue saturation value. This is commonly used in vision because the value in saturation, the value accounts for light and the saturation accounts for saturation, and it isolates these variables. Therefore, by thresholding for all values of these variables, we were able to account for all light settings. The next step in our pipeline is thresholding, which runs each individual pixel through a threshold. Now for this threshold, we focus on the hue, which is the color of the ring, minus the value in saturation. Therefore, by focusing on the hue of orange, we were able to detect rings fairly consistently. After running through the threshold, our program converted each individual pixel to a binary value of 0 or 1, as you can see on the right. This binary picture highlighted all pixels of the ring that were detected in white. Then by counting the binary pixels, we were able to figure out what type of ring we had. We created a control loop state machine. These control loop state machines allowed us to correct for any external error caused by factors we could not control. This made for a more accurate autonomous and teleop portion. We maintained shooting angle using the IMU, shooting speed using proportional and feed-forward control from the encoders, drift correction using the IMU during autonomous, acceleration deceleration using the encoders and calculating for distance. This function locks the angle of the robot, meaning that the robot will proportionally apply control to return to its intended angle despite any external interference. This is extremely useful while shooting and is also implemented in autonomous to prevent robot collisions from completely messing up our autonomous and teleop portions. For accurate shooting, we used a proportional and feed-forward control with our flywheel. Using a graphing tool, we finely tuned these values in order to make our shooter efficient. As you see, these dips in the graph are when it shoots rings, and in less than half a second, our shooter is able to recover. The feed-forward part of the control uses the constraints of the shooter system to automatically calculate the required RPM and send the shooter that power. On the other hand, the proportional values adjust for any error that might occur, including shooting rings. This also allows us press the button, the shooter automatically adjusts the speed, and will change the three angles and separately shoot down all three power cells. We have a distance sensor, which allows us to detect rings as they enter the robot. Therefore, as we're intaking rings, the robot will automatically stop the intake as soon as 3 rings are entered. It says 3. Why is it running? We also have driver sensor control, which uses the IMU, so that whatever way the robot is facing, forward is also always forward for the driver. The button, drivers can also automatically pick up and drop the ball.